All right, this is chapter 17, applications, and these problems will be all about phases and phase changes. So let's get started. We see here that we're looking at a person's lungs, and we've been given this piece of information, which is the volume of the lungs. We've been given body temperature, which is T, so we've been given temperature, and we've been given pressure, P. If we know that air is 21% oxygen, then we want to find the number of oxygen molecules that are in the lungs. And then part B, if this person climbs to the top of a mountain where the air pressure is lower, will the number of molecules in the lungs increase, decrease, or stay the same? So let's start with part A. We were given temperature, volume, and pressure and asked to find molecules. That being said, if you take a look at your equation chart, you should find that this would be an appropriate equation to use. Remember, K is Boltzmann's constant and N stands for molecules. So let's go ahead and rearrange this so that we're solving for N, and N would equal PV over KT. And we need to do a couple of things first. So first of all, since we're working with Boltzmann's constant, which has the units of joules per Kelvin, we need to make sure that all of our units, so here, 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 are going to work. Well, liters is not going to work. We want to use this meters cubed value. It says 1 liter is 10 to the negative third meters cubed. So 6 liters would just be 6.0 times 10 to the negative third meters cubed. That is a 3. And second, we do not want to work with kilopascals right here. We want to work with pascals. So that would just be 1.01 times 10 to the third pascals. Okay, so let's start plugging in our information. So pressure is this Pascal value, which is 1.01 times 10 to the third pascals. And our volume, which we just found, was 6.0 times 10 to the negative 3 meters cubed. That's going to be divided by Boltzmann's constant, so just pull that from your formula sheet, which is 1.38 times 10 to the negative 23rd joules per Kelvin. That's capital K. And our temperature, which we already have in Kelvin, and that's 310 Kelvin. All we have to do is solve for N, and when we do, we'll find 1.4 times 10 to the 23rd molecules of air. But we specifically want to know, and this is molecules of air, so we specifically want to know the oxygen molecules in the lungs. And we're told that air is about 21% oxygen. So let's take this value that we got and multiply it by the percentage. So that would be 1.4 times 10 to the 23rd molecules, and that is of air. But only 21% of these are actually oxygen molecules, so we'll multiply it by 0.21 for 21%. And our final answer here would then be 2.9 times 10 to the 22nd molecules of O2. And that would be the final answer. All right, let's go to the next one. Okay, here we see a cylindrical flask that has some cross-sectional area. And it has a piston that can slide up and down. In the flask, we have an ideal gas, and we know what the pressure is initially. And we know what the height of the piston is initially. When we add mass to the piston, we're going to see the pressure increase. And if we assume that the temperature is constant, we want to know the new height of the piston. Okay, so why don't we just kind of sketch this out first? I even made a note that it would be important to do so. So here is our cylindrical object. This isn't very good. There's a piston inside, kind of looks like that. It's at a height from the base, and it says it is 22 centimeters. And it has some area, okay? And then after, we're going to add a mass to the top. So we're going to add some kind of mass to the top of our piston. And that's going to cause the height to decrease. So some height is what we have afterwards. We want to know this new height of the piston from the base of the cylinder. Okay, so we see that the pressure is changing. And if we see that this space within the cylinder is changing, that would be volume. So we want to use P1V1 equals P2V2. Now, as you noticed, we obviously weren't given any information about the actual volume, but we were told that this is a cylinder. So if you think back to geometry, the volume of a cylinder is pi r squared h, but this is just the area. Well, we have area and we have height. Knowing that, we can actually calculate this information. I'm sorry, we have the height initially. We do not have the area, but that's not going to matter, and I'll show you why. Okay, so we have P1. Now we're going to replace V1 with A times height. So the area doesn't change of that piston. The area is going to stay the same. And that's P2, and then area again, height 2. So as you can see, these areas are going to cancel out when we rearrange the equation. We need to rearrange the equation so that we are solving for H2. And when we do that, these are going to cancel. And we're going to be left with H2. So the final height is equal to the initial height multiplied by our initial pressure over the final pressure. Okay. Now we just need to plug in the values we've been given, and we don't need to change anything. We can just leave it. So our initial height was 22 centimeters, and you can leave that. The initial pressure is 140 kPa. We can leave that as well because we don't have any other units interfering with it. And the final is 180 kPa. So kPa cancels out. We're going to be left with our height. And in this case, we're going to see that our height decreases to 17 centimeters. So that would be the answer here. All right. Next one. Number 3. Okay, we know that the atmosphere is composed mostly of nitrogen and oxygen. So for part A, is the RMS speed of N2 greater than, less than, or the same as the RMS speed of O2? And then we actually want to find the RMS speed of both of them at 293 K. All right, so the RMS speed, VRMS, we automatically know what kind of equation we're going to be using. So take a look at your chart and go ahead and find that equation, which is this. All right, so we're keeping the particles all at the same temperature. If that's the case, they're all going to have the same amount of kinetic energy because the energy of a particle is directly related to its temperature. So if the temperature is the same, then the kinetic energy should be the same as well. So we're looking at part A first. So we want to know if the speed of this is greater than, less than, or the same as the speed of O2. Okay, so temperature's not playing a role in this. They have the same amount of energy. However, this nitrogen molecule, N2, is just a little bit lighter than the oxygen molecule. So if they have the same speed, that must mean that, if they have the same energy, then that must mean that the speed of this lighter molecule is greater than the speed of this heavier molecule. Again, we say they have the same amount of energy because if we're talking about the atmosphere, and we didn't specify that there was any kind of temperature change occurring, we assume the temperature is constant, so the kinetic energy is the same. And if that's the case, then We know that the lighter molecule must be moving faster in order to keep the same energy, kinetic energy. So it's going to be greater than for this part. And then for part B, we're actually going to calculate this for each one. So for the N2, we'll start with N2. Let's just plug in the information that we know. It's the square root of 3. Okay, R is that R value. It's that constant. And that should also be written on your formula chart, which is 8.31 joules per mole Kelvin. Multiply it by our temperature, which it tells us here, 293 Kelvin. And then we need to divide it by the actual mass of the molecules. And we see here that it's 28 grams per mole. But since we're using joules, we need to go ahead and convert this to kilograms per mole. So this would actually be 0.0280 kilograms per mole. Okay, and you would find that it's 0.0280 kilograms per mole. We solved this, and you should see that the speed is 511 meters per second. Okay, so that's for the N2, the velocity, root mean square velocity of N2. So y'all go ahead and do the same for O2, and then hit play when you're ready. Okay, and after you have worked this problem out for O2, again, the only thing you're changing is this mass. So you should have found that the root mean square velocity for O2 is equal to 478 meters per second. And that is consistent with what we said earlier, that the speed must be greater for the N2. All right, let's move right along to the next problem. All right, so in this next example that I'm going to work, we're looking at a person walking through an airport, and they're carrying a duffel bag in just one hand. So we're going to consider the bone in the arm, called the humerus, and we're saying that it supports the entire weight of the bag. So we want to know by what amount the bone actually stretches in this example. The amount that it stretches would be delta L, the change in the length. So that being said, if we're looking for delta L and we know there's some kind of stretching going on, there's a couple of formulas we could choose from. But since we have a bone, here's my bone. It's a terrible bone. The stretching is coming only from one end. That means we need to choose the equation that involves stretching from only one end, which is the force is equal to Y, which is Young's modulus times the change in length times the original length multiplied by the area. Let's go ahead and rearrange this because we want to solve for delta L. So when we do that, we'll find that delta L is equal to the force multiplied by the initial length divided by Young's modulus times the area. Now, you might be asking, what is the force? Well, if the person, so here's our person, the person is carrying the bag in their arm, in their hand, then the force is just going to be, well, the force pulling down on the arm is going to be whatever the weight of this bag is. Remember, weight is mass times gravity, so mg. So let's replace the F with mg, and we get mg multiplied by the initial length divided by Young's modulus times the area. Now we really just need to plug in our information, and we will need to look up the Young's modulus value for this particular problem. So for this, we know that M is 21 kilograms. So we're just plugging in and solving now. We know what gravity is. It's 9.81 meters per second squared. And then we're going to multiply that by our initial length, which is 33 centimeters. Okay, we just used meters per second squared, so we need to convert 33 centimeters to meters, which would be 0.33 meters. So let's plug that in. Divided by the Young's modulus. Again, we can look that up. So it's 1.6 times 10 to the 10 Newton per meter squared. And then we need to use the area, which we're told here the cross-sectional area is 5.2 times 10 to the negative 4 meters squared. Once we solve this, we'll find that the change in length of that bone was 8.3 times 10 to the negative 6 meters. So that's a very, very small change. But it is a change nonetheless. I bet you didn't know that your bones stretched just a little bit when you carry something heavy in your hand. Or anything at all, really, as long as the force is pulling downward. So this image was not good. I guess I should have just drawn an arm holding a bag. There we go. That would have been a better drawing, not this. Okay, sorry. So there is our answer for this problem. Go to the next one. Oh, I even had the image right here. I just forgot to show you. Okay, that's all right. Now we'll go to the next problem. So in this next problem, we're just going to consider it conceptually. We don't need to do any math. So we have water at 100 degrees Celsius and we have steam at 100 degrees Celsius, because remember, we can have two phases at once at the same temperature. We know that we can be burned by boiling water, and we know that we can be burned by steam. But we want to know which burn would be more severe, the one caused by the water at 100 degrees Celsius or the one caused by the steam at 100 degrees Celsius. So let's consider what happens. Anytime something hot comes into contact with something cooler, those two things are going to eventually reach a thermal equilibrium where the temperature is the same. So the hotter object, the object at a higher temperature, would have to give off energy in order to come to equilibrium with the cooler object, and that cooler object would have to gain energy so they would come to an equilibrium. Well, for water, if it came into contact with somebody's skin, the water is going to give off heat. As soon as it hits that person's skin, it starts giving off heat so that it can come to thermal equilibrium with the skin. And the skin temperature is probably around 34 degrees Celsius, 33, 35, somewhere in there. So it's going to give off heat until it cools to body temperature. Now for the steam, so this is the water. The steam is also going to have to do that. So the steam will have to give off heat. Oh, I don't know why I drew that there. It gives off heat. But it's going to have to do so for two reasons. Number one, steam has to first condense back to water. So it has to give off enough heat that it can condense back to water. And then two, once it's now in the water state, then it can come to thermal equilibrium with the skin. So this one is giving off more heat when it hits your skin. If it's giving off more heat, that means that the severity is going to be more from the steam than from the water. And that's all we're doing here. Okay, now we're going to look at steam again. So to make steam, we add some amount of heat, this many joules of heat, to this mass of water. The water is initially at 50 degrees Celsius, and we want to find the final temperature of the steam. So this problem is actually going to be a little bit more involved, even though it might seem very simple to begin with. That's because we have multiple things happening. So recall that anytime we have something turning to steam, so we're going from water to steam, that we have on the curve, we have the part where it's water, and then we have this flat area where it's converting from water to steam, and then it continues on being steam. So this is steam, this is water, and this is our place where it's converting from water to steam. All right. So the first thing we need to do is we need to find out how much heat needs to be added to the water to heat it up to 100 degrees Celsius, which is the point where this can begin. So this point would be 100 degrees Celsius. We're still at 100 degrees Celsius here. But we need to know initially how much heat has to be added to get our water to begin the phase change process. Well, we can use the same formula we talked about last week, Q equals MCAT, MC delta T. So let's plug in everything we know, which is 0.220 kilograms. And then we have the specific heat of water. That should also be in one of your charts. 4186 joules per kilogram degrees Celsius, multiplied by the change in temperature. So we started at 50 and we're going to 100. So that would be the final, which is 100, minus the initial, which is 50. Okay, so 100 minus 50 is 50. You do that math and you'll find that the Q, and I guess I should label, I'm just going to call this, we'll just call this Q1, is going to be 4.60 times 10 to the fourth joules. Okay, now we're going to have to find a second Q value. And this time we need to know how much heat has to be added once we've hit this 100 degrees Celsius point. How much heat has to be added here in order to get it to fully convert to steam? So we'll call that Q2. Now remember, we're not going to use the same Q formula for this one. Since we're staying at the same temperature, we can't use Q equals MCAT because this value would go to 0 and it would cause the whole thing to equal 0. We have to use that Q equation for latent heat. So Q equals ML here. Okay, so let's plug in the information and you can just look up that value, which would be 0.220 kilograms. And then this would be 22.6 times 10 to the fifth joules per kilogram. Wow, that is let me erase that. That looks very bad. Okay, there we go. That looks more like a 10. That's to the fifth. Okay, so our Q2 comes out to 4.97 times 10 to the fifth joules. All right, so there's my Q1, the amount of heat needed to get the water from here to start the conversion to steam process. And then Q2 is the heat needed to get across this point to get to the next point. So now for step 3. Okay, so we know how much heat has already been added to the system. And then we know how much needed to be added in order to get from this point to this point and from this point to this point. So let's go ahead and subtract this value and this value from this value to see how much heat still needs to be added to the system in order to get the water to convert to steam. So we'll call that value Q3. So this is the amount that still needs to be added. So that's 5.60 times 10 to the fifth joules. Then we're going to subtract this one, 4.60 times 10 to the fourth joules minus 4.97 times 10 to the fifth joules. After we subtract these, you should find a value of 17,000 joules. Okay, so that's how much heat still needs to be added. Or that's how much heat is left over. Okay, so now that we have this, we can now go back to using this first equation because we've started back on this curve. So when we're on this part and this part, we can use Q equals MCAT, but when we're on this flat part, we have to use the formula for latent heat. So we have our final amount, and that's going to be the third Q3 equals MCAT. Okay, so let's plug in. We have 17,000 joules, and that's equal to MC delta T. Okay, so we want to know the final temperature, so we need to find that delta T value. So when we do this, we're going to get 0.220 kilograms, and then our value, and this is the C value for steam. This one was for water. Okay, so for steam, it's 2010 joules. Oh, sorry, joules per kilogram degree Celsius. Then we have delta T over here. So we're going to solve for delta T. And when we do, we should find that delta T is equal to 38 degrees Celsius. So there has been a change of 38 degrees Celsius. Well, we know that the final temperature of steam is, well, initially it's at 100 degrees Celsius. All steam has to be at least 100 degrees Celsius, but we have an additional 38 degrees Celsius here. So that means the final temperature of our steam is 138 degrees Celsius. So that was actually quite a bit of work. Not really a lot of work, but it was several steps, and it can be hard to keep track of all those steps. So be sure to label your Q values accordingly. Okay. And one more, and this will be the last problem. So we have a punch bowl that's holding lemonade, which honestly, lemonade is mostly just water with some lemon flavoring and maybe some sugar. It's at 20 degrees Celsius. We're going to add an ice cube that has a mass of 0.0450 kilograms. So this is not a large ice cube. And that ice cube, since it's frozen, is initially at 0 degrees Celsius. What will the final temperature of the system be, and how much ice will remain when the system reaches equilibrium? All right, so we're going to have to do several steps for this one as well. First of all, step one, so first let's find the heat that's lost by the water if we cool that water to 0 degrees Celsius. And remember, we're just going to say that the lemonade, since it's mostly water, we're just going to call it water. All right, so if we're cooling it, that means we're somewhere on the slanted, on one of these portions of the curve. We are not on this flat part. So we can use Q equals MC delta T. Okay, so let's go ahead and plug in what we know. And this is for the water, not for the ice cube. So Q for the water, which I'll label that as QW here. That'll make more sense. It's going to be 3.95 kilograms multiplied by C. Remember, C for water is 4186 joules per kilogram degree Celsius. And our temperature change is going to be 20 degrees. So we know it's at 20 to begin with, and we want to see what would happen to get it to 0 degrees Celsius. So that's going to be a change of 20 degrees Celsius. So the Q of the water will come out to 3.31 times 10 to the 5th joules. So that's how much heat is lost by the water as it cools down. So in order to cool itself down. Now we need to calculate a second value. We need to figure out how much heat was needed to melt the ice. All right, to melt the ice. So that's to take the ice from this point to this point. So we're here on this flat part. We're melting the ice, the act of changing phases. That means we're going to use the Q equals mL equation. And this is for the ice. And that's for the ice, and then that's the L value. So here, for the ice, it's 0.0450 kilograms. And this L value, which we can look up, is 33.5 times 10 to the fourth joules per kilogram. So the Q value for ice comes to 1.51 times 10 to the fourth joules. Okay, step 3. Let's figure out how much heat is left over at this point. So after we have taken whatever heat was needed to get the water to 0 degrees, and then whatever heat was needed to convert the ice, to change that into water to melt it, we're going to see what's left over after that. So that's going to be this value minus this value. And when you do that, you should find a value of 3.16 times 10 to the fifth joules. So we're going to call that our Q. So this is how much heat is left over after both these two processes have occurred. So let's use this remaining value of Q to warm the entire system. So that's the water plus the ice to the final temperature. All right, so we're back on this path. So we can go back to using Q equals mc delta T. But remember, this time we're looking at the whole system, so we have to add these masses together. So step 4, we're going to use Q equals mc delta T. And we need to find the delta T value again. So we have delta T equals Q over mc. And this is the total mass this time. So we're putting it all together. This was individually the water, individually the ice. Now we're putting everything together. So the Q is 3.16 times 10 to the fifth joules divided by the total mass, which is 3.95 plus 0.0450, which I'm going to write out so you don't get confused, times C. Okay, so the ice has melted at this point, so we can use the C value for water, and that's joules per kilogram degrees Celsius. So our delta T is 18.9 degrees Celsius. So we want to know the final temperature of the whole system after this process has occurred. Well, the final temperature, okay, so our final temperature, so we're going to do this last step, step 5. Final temperature is going to be 0, because we want to see what's happening with the ice, if there's going to be any ice. So it's going to be 0 degrees Celsius plus 18.9 degrees Celsius equals 18.9 degrees Celsius. So that's what would have happened to our ice, which is now water. And we see that the water started at 20 and ended up at the final temperature of 18.9 degrees Celsius, so it didn't change very much. So with that being said, because this was such a small piece of ice, there's not going to be any ice remaining after the system reaches equilibrium, because obviously 18.9 degrees Celsius is nowhere close to 0 degrees Celsius, so this ice will just now be water and part of the system. That concludes this applications video. So if you have any questions, please reach out and I'll be happy to answer them. I hope y'all have a wonderful Thanksgiving break, and we'll be back with our final unit after Thanksgiving break. Have a great day.